A wave rolls onto a dark beach, and instead of white foam, it explodes in electric blue. Step into it, and your feet leave glowing footprints. Drag your hand through the water, and the ocean draws light around your fingers. It looks like someone plugged the shoreline into the sky. But the glow is not magic. It is not radiation. And the water itself is not shining. You are seeing living organisms flash because the ocean moved. The strangest part is that this glowing wave is usually made from creatures so small you could stare straight through the water and never notice them. Many are dinoflagellates, single-celled marine organisms drifting near the surface. By day, a dense bloom of them can make the water look rusty, reddish, or brown. By night, when a wave breaks, those same tiny cells can turn the surf into blue fire. So the mystery is not just why the ocean glows. The better question is why a microscopic organism would carry a flash of light inside its body, and why it fires that flash the instant something touches it. To understand the glowing ocean, shrink the beach down until one drop of water becomes a world. Inside that drop, a dinoflagellate is not just a speck, it is a tiny, living machine. Some use whip-like flagella to spin and swim. Some can photosynthesize in sunlight. Some feed on other microscopic life. And some keep a chemical light system packed near the edges of the cell, ready to fire. The light is called bioluminescence, which simply means living light. It is produced by chemistry inside an organism. In many glowing creatures, the basic idea is a light-making molecule called luciferin, an enzyme called luciferase, and oxygen. When the reaction is triggered, energy is released as a photon, a particle of light. That is why the glow can look so clean and unreal. It is not a hot ember. It is not flame. It is chemical light made with very little heat, a living spark. In dinoflagellates, the reaction happens in tiny compartments, often called scintillans. Think of them as microscopic flash pockets. They hold the ingredients in a controlled state, almost like a camera flash waiting behind a closed circuit. The cell does not glow constantly, because constant glowing would waste energy and reveal its position for no reason. Instead, it waits for force. When water moves gently around a dinoflagellate, nothing dramatic may happen. But when the cell is bent, squeezed, swirled, or hit by sudden turbulence, the membrane feels that mechanical stress. A breaking wave creates it. A swimming fish creates it. A paddle, a hand, a boat hull, or a predator grabbing the cell can create it. That physical disturbance becomes a biochemical signal. Inside the cell, conditions change. The light-making compartments become more acidic. The enzyme turns active. The luciferin reacts with oxygen. And for a fraction of a second, the cell flashes blue. One cell is tiny. One flash is tiny. But a bloom can contain enormous numbers of these organisms. Now imagine millions of microscopic flashbulbs suspended in the same wave. The front of the wave curls. The water crashes. The cells are shaken all at once. Suddenly, the whole moving edge of the surf lights up. That is why the glow traces motion. Still water can look black. Then a fish darts through it and a blue streak appears. A dolphin swims through a bloom and its body becomes outlined in light. A person kicks the surface and every splash becomes a glowing burst. The ocean is not glowing evenly. It is revealing where it has been disturbed. The glow is a map of motion. And this is where the beautiful beach scene becomes a survival story. A dinoflagellate is microscopic. It cannot bite a fish. It cannot outrun every predator. One of its biggest threats is a tiny crustacean called a copepod, a grazing animal that eats plankton. To the copepod, a dinoflagellate is food. To the dinoflagellate, the copepod is a monster. If the copepod attacks in darkness, the dinoflagellate has one dramatic option: flash. That flash may startle the grazer for just long enough to interrupt the attack. But there is another idea that makes the glow even stranger. It is sometimes called the burglar alarm hypothesis. If a copepod grabs glowing prey, the flash may make the copepod visible to something bigger, like a small fish. In other words, the dinoflagellate may defend itself by turning on the lights around its attacker. The tiny prey cannot fight the predator directly, so it calls attention to the predator's predator. That makes a glowing wave feel different. Those blue sparkles are not decoration. Many of them are alarm signals. Every flash says something touched me. This is a pattern all over the ocean. Light is not rare underwater. On land, glowing animals feel unusual because we mostly think of fireflies. In the sea, especially away from sunlight, making light is one of the most useful tricks life has ever invented. The ocean is full of animals that use light to solve problems. Some use it for defense. A shrimp can release a glowing cloud into the water, like a luminous smokescreen, confusing an attacker while the shrimp escapes. Some squid use light underneath their bodies to match the faint glow coming down from the surface. From below, their silhouettes disappear into the dim blue above them. That is camouflage, made from light. Some animals use light to hunt. The anglerfish is the famous example, hanging a glowing lure in the darkness so prey comes closer to the mouth that was waiting behind it. Other predators use light to search, signal, or confuse. Some use light to communicate. In the blackwater, a glow can say, "Come here," "Stay away," "I am one of your kind," or "I am not worth attacking." In the deep sea, where sunlight fades to nothing, bioluminescence becomes a language. But at the shoreline, the language is being shouted by tiny cells in the surf. The reason the color is usually blue or blue-green is also not random. Seawater absorbs many colors quickly, but blue light travels especially well through water. If you are an organism trying to send a visible signal in the ocean, blue is a powerful color. It carries through the dark. That is why the glow looks so supernatural to human eyes. On a beach at night, we expect the ocean to be black. We expect waves to show up only as pale foam. Then, a breaker hits the sand and releases a color that seems too bright to belong there. But to the organisms making it, the flash is not meant to impress people. It is a response to pressure, danger, and contact. A glowing shoreline usually needs the right conditions. The organisms have to be present in high numbers. Water movement, nutrients, currents, temperature, and local conditions can help create a bloom. Sometimes these blooms are called red tides because the same dense patches that glow blue at night can tint the water reddish or brownish during the day. That name can be misleading. A red tide is not always red. It is not always caused by the same species. And not every bloom is harmless. Some algal blooms can produce toxins or create poor water conditions for fish and other marine life. So the glowing ocean can be breathtaking and still be part of a complicated biological event. Beautiful does not always mean safe. But the biology behind the glow is real and precise. Disturb the water and the flash appears. Stop moving and it fades. Push your hand forward and the light wraps around your fingers. Pull it back and the darkness closes again. That moment feels interactive, almost like the ocean is responding to you personally. But the cells are not recognizing you. They are responding to force. To them, your hand is just another sudden disturbance in a dangerous liquid world. Their universe is made of currents, mouths, turbulence, shadows, and chemical cues. A calm patch of water can turn violent in an instant when a grazer sweeps through. A feeding current can pull them toward jaws. A wave can tumble them end over end. In that world, touch matters. So they evolved a switch that turns touch into light. Now picture the same event from above the beach. A black ocean, a line of waves, a swimmer moving through the shallows. Every kick draws a blue outline. Every breaking crest sparks and vanishes. It looks like the water is alive because it is alive, just not as one creature. It is alive as a crowd. Each sparkle is a single living cell reacting for a moment. Each glowing wave is a synchronized accident caused by millions of separate organisms being shaken together. The wave is not one giant lamp. It is a stadium of microscopic alarms going off at once. And the effect lasts only because the ocean keeps moving. Breakers fold over, sand pulls water back, fish flick their tails, hands slice through the surface. Every motion writes a temporary blue sentence, and the sea erases it immediately. That is the real reason bioluminescent water feels impossible. We are used to light coming from the sun, the moon, fire, lightning, or electricity. We are not used to light appearing because a living cell was bumped. But in the ocean, light can be a shield, a lure, a warning, a disguise, a message, a trap, a panic signal. The glowing beach is only the part we can easily see from shore. Farther out and deeper down, the same basic idea becomes one of the ocean's major survival tools. In the deep, animals do not just live in darkness. They use darkness as the background for signals. A flash can expose an enemy. A dotted pattern can identify a mate. A glowing lure can turn curiosity into dinner. A soft underside glow can erase a body from view. Life did not wait for humans to invent lights. The ocean built them into bodies. So the next time a wave glows blue at night, do not imagine the water itself has changed into something supernatural. Imagine billions of tiny organisms suspended in the surf, each carrying a chemical flash, each waiting for the moment the world around it shakes. A wave crashes. The cells feel the force. Their chemistry flips on. And for one blue second, the ocean reveals the invisible panic of microscopic life.